and then connect the voltmeter parallel to the cell, the negative terminal, the negative part, the positive terminal to the positive terminal of the cell. Now adjust the rheostat to have maximum resistance. Remember that after every action of taking readings, remove or open the switch in order not to cause heating in the circuit. After connection, close the key and take the readings at the ammeter and voltmeter. Adjust the rheostat to get another set of values. Read the ammeter reading and the voltmeter reading. So, then 2.7. Adjust the rheostat and continue doing so to obtain more than 3 readings. Now, after obtaining these results on the table of results, then use the results to draw the graph of potential difference versus current. The interpretation of the graph, we find the gradient of the graph to be the change in potential difference over change in current. As we have seen here, it is two point eight minus 2.1 over 0.27 minus 0.7. This comes to be 0.43, but negative. It is 0.27 minus 7. So if you go on with this arithmetic, you will get 1.6 to something like 8, approximately 1.63 ohms. Now the interpretation is that our graph is the potential difference versus current, which means EMF in the circuit is equal to the potential drops in the circuits, in the whole circuit. Changing this one here, we have potential drop equals to EMF minus the internal resistance and times I. The graph of which you have drawn is potential drop versus current, and it's this one here, whereby our voltage intercept, the vertical intercept, represents the EMF of the cell, and the slope represents the internal resistance of the circuit. So the EMF is equal to the potential difference and the intercept. This is called the EMF of a cell, while the internal resistance is the slope of the graph.
Any conductor that is used to provide a known value of resistance in a circuit is called a standard resistor. The primary purpose of the resistor is to control the amount of the current flowing in the circuit. The aim of the experiment is to determine the unknown resistance by using a Wheatstone bridge. Requirements: 3 standard resistors, which are resistor P, resistor R, and resistor Q. Unknown resistor X, switch, galvanometer, dry cell, and connecting wires. Precaution: a switch is usually incorporated in the circuit in series with the cell to prevent the current flowing through the bridge at the point than the balance point. Procedure: connect the devices as shown in the circuit diagram. Before connecting, arrange the devices as shown in the circuit diagram. Take resistor P, resistor R, unknown resistor X, resistor Q, which is a resistance box, galvanometer, dry cell, and a switch. Then after arranging them, start to connect one device to another by using connecting wires. From resistor R to one pole from resistor P, combine one terminal of resistor P and R together. From another terminal of resistor P to the terminal of resistor Q, then combine resistor P and Q together. From one terminal of resistor Q to unknown resistor X, from unknown resistor X to the terminal of resistor R. From the point where resistor P and resistor R meet, connect to the positive terminal of galvanometer. From the negative terminal of galvanometer, connect to the point where resistor Q and resistor X meet. Then, from the point where resistor R and X meet, connect to the negative terminal of a dry cell. From the positive terminal of dry cell, connect to the switch. From the switch to the point where resistor P and resistor Q meet. After connecting, close the circuit and observe what happened in galvanometer. It observed that a galvanometer deflects in one side. Remove the plug in resistance box one by another until a galvanometer reads 0 mark. Record the value of resistor Q, which is equal to 10 ohm. Then, from the circuit diagram, the potential difference across AB is the same as potential difference across AC. And again, the potential difference across BD is the same as potential difference across CD. Now, by using a formula, make a relation of expression number 1 and expression number 2 in terms of ratios, which is equal to VAB, VAC, and VBD is equal to VCD. Now, VAB over VBD is equal to VAC over VCD, whereby V is equal to current I times resistance R. Now, from the circuit diagram, it means that there is a flowing of current. Here we have total current I. When it reaches at point A, the current divided into 2 parts. One is Y1, which passing through resistor P to the resistor R, and another is I2, which passing through resistor Q through resistor X. Now, it means that in the part of VAB, the current here will be equal to I1. And in the part of BD, the current also is I1. The same ways in the part of AC is I2, and CD also is I2. But note that this relation is used when there is no current flowing in the galvanometer. Now, instead of VAB over VBD, which is equal to VAC over VCD, substitute the value of V in each value. This will be equal to I1 P over I1 R, which is equal to I2 Q over I2 X. When you simplify this, the answer will be equal to P over R, which is equal to Q over X. Now from there, make X to be the subject because we are required to find the value of unknown resistor X. This will be equal to X is equal to R Q over P. Now, the value of R we have, which is 2 ohm times the value of Q is this one, 2 ohms times 10 ohms over P. The value of resistor P is equal to 4 ohm. Then simplify the expression here by 2 1, by 2 2, by 2 1, by 2 5. Ohm goes. The answer here is 5 ohm. Therefore, the value of resistor X is equal to 5 ohm. Conclusion. The arm AB and arm BD are known as the ratio arm of the bridge. The Wheatstone bridge provides an accurate method of determining the resistance of an unknown resistor, since at balancing, no current flows in the galvanometer. From the knowledge of Wheatstone bridge, can you describe how a meter bridge is used as a modified Wheatstone bridge?
Determination of resistivity of a conductor. Introduction. Resistivity of a material is the ability of a material to oppose the flow of electric current. It depends on the material makeup, the length and cross-sectional area of that material. It is measured in ohm meter. In electrical appliances, different wires of different resistances are employed. In order to use appropriate wire, there is a need to know its resistance and resistivity, and hence the efficiency of the guard gate. The aim of this experiment is to determine the resistivity of Constantan wire. Requirements: meter bridge, sensitive center zero galvanometer, resistance box, meter rule, dry cells, a switch, Constantan wire, jock, and connecting wires. Procedure and observation. Connect the devices as per circuit diagram shown here. The positive terminal of a dry cell is connected to make end A a positive one and the other end B a negative one. Connect the negative part of the cell to the switch. Connect the positive terminal of the dry cell to the terminal A of the wire, and the negative part of the dry cell to the end B, or terminal B of the wire. Take the Constantan wire, measure it to 50, connect to the right hand gap. Connect the resistance box to the left hand gap of the meter bridge. Connect sensitive center zero galvanometer to the center of the meter bridge. Now, from the meter bridge, you connect to the galvanometer through positive terminal, and through negative, you connect to the jock. To test your circuit, take a jock and close the switch. Touch on the left hand side of the meter bridge, the deflection is there. Touch the other part. Now narrow the interval so as to get the zero balance of the balancing point, which we call X. 0.5. Now let's change the positions of the constantine wire and the resistance box. Make sure that the wire doesn't touch before it reaches the knob. Again, test for deflection. So it deflects both sides, showing that it is okay. Now find the balancing point. Okay, this is 33.2. Length L1 is measured from end A, and so 100 minus 66.5, we have length 2, which is 33.5. Okay. And for this one here, this is 8, 66. Now, find the ratio L1 over L2. Also, take L2 over L1. Afterwards, then multiply these ones by 2. There is resistance here. So we multiply by 2 to get the following. Times 2. Thereafter, add the two resistors and find the average. So the resistance of the wire is 3.997 ohms. Pick the wire and measure its length and diameter. Record. So the length is, after measuring the length of the wire, measure the diameter of the wire, at least 3 parts of the wire. Then record. The second part. The third part also. Find the average. So the diameter comes to be 0.626 millimeters. Now, the resistance is given by resistivity, length over area. We need to find the resistivity. It will be given by R times A over L, whereby area of the circle is given by pi r squared or pi d squared over 4. So our resistivity will be given by R, area, which is pi d squared over 4 over L, in which we substitute. Our R is 3.997 times pi times diameter is 0.26. Since it is in millimeters, we change to meters. 10 to the power negative 3 squared over the length is 50 centimeters, so it is times 10 to the power negative 2. Put them in meters, and then times 4. Now, calculating this one here, this comes to be 4.246 times 10 to the power negative 7 ohm meter. The resistivity of constantan wire, we have got 4.246 times 10 to the power negative 7 ohm meter. Conclusion: the resistance of a wire is directly proportional to its length at constant temperature. Resistivity is the behavior of a material which is the constant of proportionality between resistance and the length for a given cross-sectional area. Sources of error in this experiment: parallax error in a reading balancing point, and the other one is heating of the circuit due to sliding of a jaw. You must touch the wire and not slide on it. Now determine the resistance of nichrome wire and hence find its resistivity.